Thank you very much. I would like to thank the organizers for inviting me here, even the ones that are not here today. I will try to summarize a little bit the status of calculation of Relic neutrino decoupling and how can we detect them. Then in coming talks, we'll comment on non-standard physics scenarios. So I believe that most of you are quite expert in neutrinos. So I will just give a very brief introduction just to focus on what I will be talking about. This picture shows the standard model of particle physics with all the leptons, fermions, quarks, and bosons. We will only be interested basically in these three particles, the neutrinos. Neutrinos are in the standard model massless particles. We know that they are not massless because we study neutrinos at very different energies. So the main focus of the rest of the talk will be the low energy part of the spectrum, which is also the one that corresponds to a higher flux. But the neutrinos we know better are actually these ones from solar neutrinos, reactor neutrinos, atmospheric ones. These are those that basically give us information about neutrino oscillations. When we analyze all the terrestrial data about neutrinos, we obtain a global fit of neutrino oscillation properties, which are two mass splittings. And you see that the lowest mass splitting, which is also called the solar one, is known to a very good precision. The second mass splitting is known only for its absolute value. We ignore the sign. This is called the sign of the second mass ordering is what defines the neutrino mass ordering, which I will comment in a second. Then we have three mixing angles. Some of them are known very well, like θ1,3 and θ1,2. We still have some uncertainty about the octant of θ2,3, which is close to be maximal, but it's not exactly maximal. So we don't know if it's on this or on the other side. And then we have also a CP violating phase, which is known to be more or less between like pi and 1.5 pi, something like that. In coming generation of experiments, we'll of course clarify all of these remaining unknowns, but for the concern of cosmology, we are not really interested in many of the oscillation parameters I will show later. The problem of the mass ordering is quite important, at least in cosmological analysis, because we know that if the lightest neutrino is massless, we have nu1 in the normal mass ordering, then the mass of the second and of the third mass splittings are respectively about 1 millielectron volt and around, 10 millielectron volts and 50 millielectron volts. While in the inverted ordering case, it's the opposite. So the large mass splitting defines the bigger mass difference. And so the 1 and 2 mass eigenstates are very close to each other, but they are the heavy states. So they are approximately 50 millielectron volts. The blue band here represents the mixing between the mass eigenstate and the electron flavor, which is very important for direct detection of relic neutrinos. I will show later. So you see that in normal mass ordering, the lightest neutrino corresponds to the most fraction of the electron neutrino flavor, which corresponds therefore to the lightest lepton. In the inverted mass ordering, the mixing with the electron flavor is the smallest, so this is why we call it the inverted. The lightest neutrino mostly corresponds to the non-lightest leptons, let's say. So this was more or less the introduction about neutrinos, the important things that I will discuss later. Let's talk about neutrinos in the early universe. This picture shows more or less complete explanation of what we call the standard cosmological model. The Big Bang is the initial state of the universe when the plasma was very dense and very hot, then the expansion started. We have an initial phase called inflation, where the expansion is exponential. Inflation ends at some point, which is called the reheating, which will be discussed in the next talk. After reheating, we have radiation domination. During a radiation domination, all the standard model particles are first thermalized at a very high temperature, so they are in a relativistic state, but then the temperature goes down with the expansion, so the particles start to decouple. When the interactions are small enough for them to stop interacting with the rest of the plasma, for example, we have a relic of photons that freely propagates until today. This is what we observe to be the CMB, the cosmic microwave background. And we also know quite well the light abundances which come from Big Bang nucleosynthesis. What happens to neutrinos? So neutrinos are in a very hot plasma and very high interaction state in the early universe. In this plot, where time goes from right to left, you see that at very high temperatures, neutrinos have a very high interaction. This red line represents the interaction rate. And it's important to know that interactions are very frequent in the early universe, so neutrinos cannot oscillate until basically the red line falls behind these colored lines, which represent the oscillation rates. This means that basically neutrinos interact so fast that they do not have time to move from the flavor to the mass basis. When these lines cross, the oscillations start, but there is not so much time for oscillation to take place because neutrinos decouple at a temperature of approximately 1 to 2 MeV. When the expansion rate, the red line, as the black line, becomes larger than the interaction rate. This means that the neutrinos are driven apart from one another faster than they could interact. After the decoupling, the neutrinos start to propagate freely, and since the expansion of the universe decreases their energy, they basically free stream until today, when they have a temperature of approximately 2 Kelvin, which is smaller than the temperature of the cosmic microwave background, because after neutrinos decouple, electrons and positrons transfer their entropy to the photon fluid, and only in a small fraction to the neutrino fluid. The number density of relic neutrinos today is 56 per centimeter cube per family. So that means that we have approximately 300 neutrinos and antineutrinos per centimeter cube, which is the second most abundant particle in the universe after the CMB photons. So all this description is actually a little bit schematic and approximated, because in reality, the decoupling is not instantaneous. It takes place as a function of the neutrino momentum. Because the interactions are momentum dependent. So that means that the decoupling distorts the neutrino momentum distribution function. In order to compute this distortion, typically we assume what we call a density matrix formalism. The density matrix is this one. You see that it contains on the diagonal elements the momentum distribution function of the 3 neutrino flavors. The off-diagonal elements instead represent the coherency of the neutrino system. And they are particularly important when we take into account neutrino oscillations. So the evolution of the density matrix as a function of this comoving variable, which represents basically the scale factor of the universe and the comoving neutrino momentum, can be described by a set of equations which is represented here. You see that these equations contain the expansion of the universe, the Hubble factor. This term here represents the effective Hamiltonian, which describes oscillations in vacuum and oscillations in matter. Respectively, you see this term here and all this series of contributions here from leptons and neutrinos for the matter term. And then we have the collision integrals, which represent the interactions between electrons and neutrinos and between neutrinos themselves. This red term is actually the most complicated part of this set of equations, because it connects the neutrino distribution function, so the density matrix in products up to four times. So this complicates the solution of the system, but it's not terrible. We can solve it numerically. I will present the results we obtained with our Fortran code for piano. Maybe later we will hear about other approaches from Julien Frustet. So we run this fortepiano, and what we obtain is something like this. This is the evolution of the momentum distribution function divided by the Fermi-Dirac for a given neutrino momentum as a function of the scale factor. So at the beginning of the evolution, you see that we have 1, which represents the equilibrium distribution function, which is the Fermi-Dirac. Then, depending on the neutrino flavor and if we consider neutrino oscillations or not, we can have a different increase in the momentum distribution function of this specific value. And you see that typically we have that for the electron neutrino flavor, which is the dashed line, we have a higher increase with respect to the muon and tau neutrino flavors, because the electrons have more interactions with the thermal plasma. The thermal plasma is mainly constituted of electrons and photons. So it's normal that charge current interaction involve these neutrinos, while these other are just involved in neutral current interactions. If we look at the final distortion of the momentum distribution function, always with respect to the Fermi-Dirac, we have that at low momentum there is no distortion because the interactions are low, so the neutrinos with low momenta decouple earlier. While at large momenta, you see that you can have up to 10% or 20% of increase. When we want to compute the distribution function, of course, we are interested mainly in integrating it because we want, for example, the energy density of neutrinos in order to compute, for example, the effective number of relativistic species. This is the energy density of neutrinos divided by the one of photons, and it involves the integral of the momentum distribution function, which is multiplied by the third cube of the momentum, which suppresses the integral at low momenta. And the Fermi-Dirac term instead suppresses the high momenta. So the main contribution to an effective actually comes from a range of momenta between something like 1 and 5, more or less. This means that if we have a 10% increase on this side, it's actually the suppressed side. The most relevant region is this one. And indeed, if we compute an effective as a function of the scale factor, we see that it starts at 3 when the neutrinos are in equilibrium. But then after neutrino decoupling and after part of the energy density from electrons and positrons is transferred to the neutrinos, we have 3.044. This is the reference number and it's quite stable. We studied it as a function, for example, of neutrino oscillation parameters. You see that the colored bands represent the results from the global fit I presented at the beginning, and the lines represent how much an effective is sensitive to these parameters. You see that there is basically any difference between different values of the mass splittings and most of the mixing angles. The only mixing angle that's actually impacting a little bit an effective is the one represented in red, which is theta 1, 2. But the effect is very small, up to 10 to the minus 4 approximately. So it's quite safe to say that an effective is 3.044 plus minus smaller number than 10 to the minus 4. If you followed a little bit, or if you are accustomed to the literature, you probably remember a different number. So this 3.046 was the first 3-neutrino calculation to take into account the neutrino oscillation pattern completely. This was 2005, and Sergio was involved in this paper. Then Sergio was also involved in this paper, where together with Pablo Fernandez, they updated the collision terms and got 3.045. Then in 2029, Yvonne, together with other collaborators, computed for the first time the third order corrections to finite temporal quantum electrodynamics, which lowers the N effective by another 10 to the minus 3. And then last year, there was a paper by people in Naples claiming that an effective is actually 3.043 because of next to leader and order corrections to interaction rates. But Yvonne actually presented a paper that disputed a little bit this result, and it was confirmed to be 3.044 up to the best knowledge we have today. This is in perfect agreement with, for example, cosmological constraints by Planck. You see here the region preferred by CMB is centered around 3 with a quite significant error with respect to the difference we have between 3 and 3.044. So we are not yet at the level of distinguishing the non-instantaneous decoupling effects. But this measurement is indeed important because it confirms that there are 3 neutrino-like relativistic species in the early universe. So these can be neutrinos or other particles, but we know they are there. So it's an indirect confirmation that neutrinos may be present according to our cosmological model. What if we want a direct confirmation instead of having just an indirect probe through the energy density? And this is the topic of what remains of my talk. So the direct detection of relic neutrinos is actually very complicated. We would like to have something like this, which is the map of the cosmic microwave background, the anisotropies. And it's impressive how in 30 years from COBE, we arrived to the Planck map. The improvement is huge. This is the map we have for neutrinos. We have no neutrinos. So it's actually not surprising. The interactions of photons are much, much higher than the interactions of neutrinos, especially neutrinos with the energy we are talking about, order 10 to the minus 4 electron volts. If you remember the minimal value of the mass for the second order, this is right? Okay. It's above 10 milli-electron volts. So here it means that the energy is much lower than the neutrino mass. These are non-relativistic neutrinos. We never detected interactions of non-relativistic neutrinos. So it's not surprising that it's very tricky to get them. There have been several proposals in the past that tried to propose a mechanism for detecting the interaction of these non-relativistic neutrinos. I will go through some of them. There are basically two main ways. One is through elastic scattering and one is through inelastic scattering. So in the case, for example, of elastic scattering, we can have, for example, the interaction of relic neutrinos with some detector, and Stodolsky proposed in '74 a mechanism that actually works only if there is neutrino, anti-neutrino asymmetry. The idea is that if you have an electron, the interaction between the electron and the cosmic neutrino background splits the energy density, the energy states of the two electron spins. The up and the down spin will not have the same energy. That means that the electron gets a torque. If you build a ferromagnet with all the electrons aligned and so on, you maybe can get this torque due to the movement of the electron in the cosmic neutrino background, and try to see if you can measure it. Solution? No, not a solution. You see that the expected torque is 10 to the minus 26. Well, at least at the time of this paper, the best sensitivity of torsion balances was 10 to the minus 12. So we are very far away from the expected signal. In the last years, there was a lot of discussion about this process called coherent elastic neutrino nuclear scattering, which has been detected for the first time in terrestrial experiments. So the idea is that if the neutrino have a very small energy, then instead of interacting just with one nucleon at a time or one quark at a time, it sees a whole nucleus or even a bunch of nucleus in a coherent way. So instead of interacting just with one of them, interacts with all of them. That means that the cross-section gets an enhancement which is proportional to the number of nucleons in the coherent volume. Since the coherent volume depends on the neutrino energy, for lower energies we have a larger coherent volume, so a larger increase of the cross-section. Applying this to cosmic neutrinos, to the cosmic neutrino background, it's actually a possibly nice idea. You see in this plot, basically the expected acceleration produced on some target by the scattering of coherent neutrinos as a function of the lightest neutrino mass, for different assumptions about the neutrino momentum distribution function. But if we consider the standard one, which is the orange region, you see that we may get even a factor 10 to the 3 enhancement in the expected signal. Unfortunately, this is still far below even the proposed torsion balances mechanisms. For example, future torsion balances are expected to reach 10 to the minus 23 in sensitivity. Yeah, well, still 4 orders of magnitude away from this range. Still nice try. Let's see another one. Another possibility, instead of having the coherent scattering and trying to measure a torque, we can have we can try to measure oscillations. The idea again is the same. If we have a flux of cosmic neutrino background, that will generate an oscillation of the target, which, for example, is a pendulum. If we put this pendulum on interferometers, we can try to detect the small variation of distances here just by using the same principle we use for gravitational waves. Yeah, well, also this time it's not really optimistic. You see that the sensitivity of LIGO, Virgo, and Kagra are represented here. The signal is, again, several orders of magnitude below. And this more or less concludes the fact that elastic scattering doesn't work. Let's try with different method. This method is actually older than all the other ones that I presented here. Was proposed the first time by Weinberg in '62. Weinberg proposed it for massless neutrinos, but it actually works for massive neutrinos even better. The idea is to have some nucleus which can undergo beta decay. For example, here I represent a neutron. The neutron decays to a proton, electron, and antineutrino. Instead of the antineutrino on this side, we can put it on the other side. So the neutrino triggers the emission of the electron. Instead of having the spectrum we typically have for beta decay, which is this one, which ends at some endpoint k, in this case, we will have a small peak of events after the beta decay endpoint, because the energy of the neutrinos triggers the emission of the electron, and it's not that the electron and the antineutrino split the energy between themselves. So it's actually possible to try to measure the presence of a small peak at the end of the beta decay spectrum. The separation between the endpoint in the peak is approximately twice the mass of the lightest neutrino. So in principle, we just have to achieve a very good energy resolution. The peak is very small, so we also have to achieve a big detector with a lot of decaying material, which is not trivial, but I will discuss it later. You see also in this plot that if and only if there are sterile neutrinos, it's probably easier to detect them, because depending on their momentum distribution function, they may have a sufficiently large number density, and in that case, the separation between the endpoint of beta decay and the peak due to the sterile neutrino is much larger than the lightest neutrino mass. It's actually proportional to the mass of the fourth mass eigenstate. I said we need a lot of material. Which material? So this has been studied in 2007 by people in Naples. They built a very large table with a lot of possible beta decaying substances, and at the end they concluded that the best material is the one that has the largest cross sections time velocity times half-life. And among these two candidates are the ones that best satisfy this relationship. But at the end, we select the tritium because their higher cross-section means that we have a larger number of events. So if we build a detector with tritium, we can simulate the beta decay spectrum and the neutrino capture spectra. So you see here we have the formula for the neutrino capture event rate. You see that it contains the mixing matrix element corresponding to the mixing between the mass eigenstate and the electron flavor, because at the end we detect electron neutrinos. This therefore means that the peaks due to the different mass eigenstates are weighted by the mixing with the electron flavor, and of course, depending on normal or inverted ordering, we have a different behavior. Then there is the number density in vacuum. There is a clustering factor, which is basically how much of the relic neutrinos, which are evenly distributed in the early universe, cluster around the matter distribution of the Milky Way or of the local clusters and so on. And similar behavior we have for the beta decay spectrum. There is, well, this is a function of the neutrino masses, but we have here the mixing between the electron flavor and the mass eigenstate. So one of the crucial parameters in order to determine if we are able to distinguish the relic neutrinos or not is the sigma, which is the energy resolution of the experiment. Here I show two plots for the same lightest neutrino mass, 10 millielectron volts, and two different energy resolutions. So 10 millielectron volts versus 50 millielectron volts. You see that there is a huge beta decay spectrum here, which is much, much larger than the peaks due to the capture on relic neutrinos. This kink here is due to the fact that inverted ordering, the second and the third mass eigenstate just contribute to this part of the energy range. So we have a sharp kink, which actually could be measured in order to determine if the mass ordering is normal or inverted. And then you see that the red spectrum, which is the one corresponding to normal ordering, has a higher first peak closer to the beta decay spectrum and a lower second peak, while the inverted ordering is the opposite. This peak is actually the one that corresponds to nu3, which is the smallest mixing matrix element, while the second and the third lightest mass eigenstates have the largest mixing with the electron flavor. So it's actually a little bit higher, a little bit easier to determine if there are relic neutrinos or not in the inverted ordering case. Unfortunately, data seem to prefer normal ordering, but this is another story. In any case, you see very well here that the separation that we can get with 10 millielectron volts of energy resolution is completely lost if we have 50 millielectron volts. So it's actually very crucial to be able to achieve a very good energy resolution in the experiment. Otherwise, no matter how many relic neutrinos we have, the beta decay spectrum will be much, much higher, and we cannot see the interesting events. So in summary, we have this proposal or early stage experiment, which is ongoing at Gran Sasso Laboratories in Italy. This is called the Ptolemy experiment. It tries to build a detector with 100 grams of atomic tritium in order to detect the relic neutrinos with an energy resolution of probably around 50 to 100 millielectron volts. And corresponding to the numbers we have, that corresponds to a few events per year, which is not much. I will not have time to discuss how many neutrinos there are here with respect to the mean empty universe or other types of enhancement, which, however, cannot really increase this number by orders of magnitude. This may be a factor of 2 or something like that. I will summarize a little bit of the Ptolemy structure just to give an idea and comment on another few points. So Catherine is basically designed to measure the endpoint of beta decay. This is the same as the Catherine experiment is currently doing to measure neutrino masses. The problem is that Catherine uses at each time a few tens of micrograms of tritium inside the detector. This is clearly not enough for the detection of relic neutrinos because we need many more tritium atoms to interact in order to have a sensible event rate. So the idea is to build a solid substratum to attach the tritium atoms on, possibly like a graphene layer, which is a flat layer of carbon atoms. On graphene, we have hydrogen atoms attached to the carbons. If we replace the hydrogen with tritium, in principle, we have a good way to store a lot of tritium in a small space. But I will discuss later, there is a problem with the Heisenberg principle. So if you have a flat layer, that will probably mean that you have a large uncertainty on the neutrino, on the electron energy, which is on the emitted electron energy. Another possibility is to use, for example, small balls of graphene, which is what we call fullerene, or tubes, nanotubes or something. In any case, once we have fixed the issues with the source, then we will have an emitted electron, or many emitted electrons, too many for them to enter the microcalorimeter that will give the final energy measurement. So we actually have to find a way to first filter away part of the electrons and then to have the final energy measurement. It's actually very interesting to implement a combination of electric and magnetic fields that actually would give first a preliminary energy determination of the electron, just for the fact that it's spiraling within these fields. This is a radio frequency antenna technique, which is actually also implemented in the Project 8 experiment for neutrino mass determinations. So nothing new, but we have to implement it here in Ptolemy. And then the same electric and magnetic field will actually filter away many of the electrons so that the microcalorimeter is not fried when the huge flux from beta decay arrives. And at the end, the few remaining electrons will go to this transition edge sensor, which is the same technology that other experiments such as ECO or OLMS are trying to use for the determination of neutrino masses. So this Ptolemy actually is taking from many of the techniques that are actually implemented in neutrino mass determination experiments and merge them. If Ptolemy is built successfully, this plot shows what's the statistical uncertainty we could get about the determination of the existence of relic neutrinos. The blue regions correspond to no detection, so that means if the neutrino mass is very small, for example, and the energy resolution is not so good. Ideally, if the neutrino mass is quite large, then we have quite easy detection if the energy resolution is not so good, but notice that these values are almost ruled out by, they are ruled out by cosmological measurements, and they are close to the current limit by Catherine. You see that the normal versus inverted ordering difference is actually only on this side of the plot, because at the end of the day, if the neutrino masses are below 50 millielectron volts, we can see the difference between the first and the second peak, or the second and the third peak. If the neutrinos masses are above 50 millielectron volts, then all the neutrino states are degenerate, and so there is no advantage in having normal versus inverted versus normal ordering. Final comment is, I was saying about the energy determination. So in principle, we would like to achieve something like 50, 100, or even better, if possible, millielectron volts in energy resolution. The problem is that if we have an electron emitted atom, it's probably something like contact. I don't know. Okay. If we know very well the position of the initial tritium atom, then we have to have a very high uncertainty on the energy of the emitted electron. This is the Heisenberg principle. So in this paper, there was a study about how different configurations of graphene or combinations of carbon atoms can actually produce a better output for the energy uncertainty. And at the end of the day, it seems that concave sites behave differently than convex sites. So a flat layer is actually the worst possible scenario. Maybe the best idea is to use a tube, a small nanotube, where you have the electrons inside. In that case, you just have one direction for the final electron to come out, and you avoid part of the uncertainty. I will not enter all the details, but you see here that in the case of the unbound tritium atom, you will have this spectrum. In case of bound tritium atom with the final free electron, which is the case that we were thinking about when the tritium atom are attached to graphene, then we will have a huge energy uncertainty. This will never allow to measure the neutrino capture. The other configuration is a stage where you have a bound tritium atom at the end, so you still know the position of the electron, but due to the suppression of the transition, you get basically a quite significant suppression of the flux, but still a good energy determination. So in principle, it's not impossible. It's just very hard to understand what's the best configuration. The true experiment will probably fall somewhere between these two cases. This brings me to the conclusions. So we are entering neutrino precision era from many sources, not yet from cosmic neutrinos. We have indirect evidence of their existence, but we still have to struggle a lot in order to have a direct detection of this neutrino background. Thank you. And if you have any questions.
Thank you very much for this very nice talk. Time for questions.
Thanks for the useful talk. However, the last two conclusions that you emphasize in this slide have been emphasized before by Roulet and Vissani before Ptolemy collaboration. This is clear from the paper. You can read already the abstract and the importance of this lightest neutrino mass, the relevance and the difficulty that it creates for the detection were emphasized before by this group, and then somehow endorsed also by Ptolemy collaboration.
Yes, yes. So there are actually many papers
No,
that
no,
I
no,
didn't
there are
discuss.
there are
No, no,
very many papers. This is the paper where this was emphasized, and not the paper of Ptolemy.
no. I mean, there are many papers that I didn't have time to discuss. And of course, the
It's
one.
not problem of time, it's problem of priority. Okay.
Yes, yes. Okay.
Other comments, questions?
Hi, Stefano. Just a curiosity, if you have some non-standard physics like decaying of neutrinos between the formation of the cosmic neutrino background with a lifetime less than the age of the universe, then Ptolemy,
We'll never detect the Relic neutrinos because they are basically gone.
yeah, because
So basically, yes, the assumption is that if neutrinos are stable, if the cosmic neutrino backgrounds decouples and then just free streams, then the energy density will actually be the same that we expect. So here we have this N0, which is 56 per centimeter cube, etc. If the neutrinos decay before we can detect them, of course, this will be 0, and so the cosmic neutrino background will never be detected.
and the other methodologies that you showed before the neutrino capture, I mean, the other methodologies that were proposed,
No, they will
No.
the same. I mean, because at the end, any methodology measures the relic neutrinos today. So if they are already gone, we will never get to measure them. There is just only some models, for example, where the heaviest neutrinos decay to the lightest one. In that case, it's maybe possible to detect them, but not probably with this technique, because if the lightest neutrino is, for example, stable and it has a 0 neutrino mass, then it will just be on the same energy as the endpoint of beta decay. And of course, even if we have a very good energy resolution, it's not possible to distinguish which neutrinos are what. In that case, the possibility is actually to use asymmetries. I don't think I have a slide, but basically, if you put the Earth, the solar system, and so on within the cosmic neutrino flux, there will be a modular, so the annual modulation or the daily modulation of the signal. And with some like fast Fourier transforms, then maybe we can try to distinguish the periodicity of the signal and to get the part that corresponds to relic neutrinos. But even in that case, it requires at least one neutrinos to be stable. Otherwise, it's impossible. If you have Kiwi sterile neutrinos, also in that case, it's the same. If they are stable, we can actually measure them even easier in the sense that the separation between the endpoint and the peak will be much harder. In that case, the problem is possibly the number density, because if the number density of relic neutrinos is, so active neutrinos is 56 per centimeter cube per family. In the case of Kiev sterile neutrinos, will be much smaller because otherwise you basically overproduce them and you saturate the universe. So there is a suppression due to the number density, but in principle, it's much easier to detect the peak. That, I mean, it will be maybe possible, but not easy in any case.
Other comments or questions? No? Okay, so if not, let us thank Stefano again.